everyone, this is Dr. Daya Sagar Chowdary, Senapati, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University-Surampalem. Today we would like to discuss about the ring counter. So coming to learning outcome, at the end of this lecture, student will be able to understand the operation of ring counter design and analyze and apply it for sequence generator and timing control in digital systems. Coming to the ring counter, so a ring counter is typically application of the shift register. That means most of the time for ring registers and counters, for these two devices, most of the time flip-flops are the basic building blocks for these two major devices. That means the ring counter is almost the same as the shift counter. Now the only change is that the output of the last flip-flop is connected to the input of the first flip-flop in the case of the ring counter, but in the case of the shift register it is taken as output. Except for this, all the other things are same. So we will discuss all these things in the slides, next slides. Now this is a simple block diagram for the ring counter. That means this ring counter contains 4 D flip-flops. That means flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3. That means it contains 4 flip-flops, so that we can simply call this one as a 4 flip-flop ring counter. That means 4 bit. It is simply rotating the bit inside the 4 bits. That means 4 times it will circulate. That means here, if the data is coming here, it will circulate to here, that is 1 step, and here that is 2 step, this is here 3 step, and this is here and 4 step. That means this is a 4-bit ring counter. Why we call this one as a ring counter means simply the output simply given to the input as a feedback. That means at the end of the last stage, we call this one as a last stage. So here Q3 is the last stage. That means the output Q3 that is directly given to the input of the first stage. That means here the first stage is D0. So D0 we are applying simply to D0. That means Q3 is equal to D0. So directly it will rotate. That means here 1 is shifted from D0 to Q0 when clock signal is 1. So likewise we have to calculate the counting part. Anyway, we will discuss in the next slides. So this is a simple ring counter contain the clock signal, that is CLK. So CLK is given to all the flip-flops. Here the point wherever we are using the clock signals, so all the flip-flops we are applying the same clock. That is why this one we call that one as a synchronous circuit. And ORI, we will discuss this ORI in the next stage. We call this one as a overriding input. So we will discuss this one also, and that is given to first flip-flop, that is PR. We call this one as a preset, and here this CLR, the second stage and the third stage and fourth stage, we call this one as a CLR. That means clear. So this is the simple connection of the total circuit. Now for a ring counter, so it is a type of digital counters used in the circuit, so typically built with flip-flop. We already discussed it in the starting position. If any register or a counter, the only thing is the flip-flops are the basic building blocks. That is why we used the D flip-flops of 4 stages. In order to calculate the 4-bit ring counter, we are using 4 stages. Here it works by shifting a 1 through a series of flip-flops, one at a time in a loop. So we will discuss each one in each slide. And number of states in the ring counter, it completely depends on the how many flip-flops we used. That is the case. So that means if we increase the number of flip-flops used in the particular ring counter, that is the bit that times that number of states, we can simply call that one in the ring counter. Number of states is increased. If we increase the flip-flop count, the number of states is also increased in the ring counter. That is the concept. Now coming to key characteristics, single bit, that is 1. So only 1 bit in the counter is set to 1 at the given time. That means we will discuss this one also. And cyclic behavior, the pattern of the bits follows a cyclic behavior and repeats after a fixed number of steps. And no reset, so the ring counter does not automatically reset to 0. Instead, it starts at a defined state and then continues cycling. So this is also we have to discuss. So now coming to the a ring counter is typically built using flip-flops. This we already discussed. So most of the time the flip-flops are like D type or T type or JK flip-flops, and it consists of n flip-flops because it depends on the number of states, that is the number of flip-flops count. So where n is the number of states in the counter. The number of flip-flops determines the number of unique states the counter will cycle through, and one bit in the counter is set to 1, the rest of the bits are set to 0. In each clock cycle, the one bit shifts through the flip-flops and the pattern repeats. This is also we can discuss in the next slides. The output of the last stage, that is last stage which flip-flop is used, that last output, that is here in this case Q3 is the last output, that is directly given to the first stage, that is D0. D0 is the first stage, that is Q3 is equal to D0, that is directly given. So fed back into the first flip-flop forming a loop, hence the name called ring counter. That means it is simply a just like ring, it follows the ring. Now coming to the 4-bit ring counter, maybe this is the we can easily analyze this ring counter concept with the help of one application. So let us start with the application. So if we use the 4-bit, that means 4 stages, that flip-flops contains 4 flip-flops. Now if we construct a circuit, let us come to the circuit diagram. So this is the simple block diagram. If this block contains 4 flip-flops and now the output is given to input, that means Q3 is directly given to input, means so that is a simple ring counter we call this one as. But the if we use the clock signal high, that means if clock signal is enabled, so the whatever the data D is 0, if Q is 0 and D1 is 0, Q1 0 and D2 is 0, Q2 is 0, D3 is 0, Q3 is 0. That means initially all the states, whatever the inputs, because D0 depends on the Q3 and Q0 depends on the D0 and Q1 depends on the D1. So if we start from initial condition, that means all the zeros, so the only zeros will rotate. We call this one as a completely zero data inside the ring counter. But we have to count, in order to work out this particular ring counter, we have to install one bit, the bit is 1. So we have to install that set, we have to set this 1 to inside the ring counter. So there is a procedure, we have to set this 1 bit inside the ring counter. We can analyze the part, and the others are set to 0. That means mostly for stage 1, the first flip-flop we are using, for first flip-flop we are setting a data 1 here. The remaining all the flip-flops we have to give the data 0. So for that particular reason we have to use this particular whatever the operation we have to enable, like initial stage. So we are giving the data 1 for the first flip-flop and 0 0 0 for the second, third and fourth flip-flop. So this we can achieve with the help of the whatever that 2 signals, that is we already used that signals, we call that one as this ORI, override input, and that is a PR, that is preset, and CLR, that is clear. So by applying the ORI is 0, so we can check that in the next slides. So this is a ORI input, that means overriding input. So now preset, this is a clear. If we use that preset signal to 0, that means if the preset signal to 0 means simply this signal preset is 0 and at the same time the same connection is given to this ORI, and all the CLR, that is clear terminals, are also connected to the ORI signal only. That means if we apply 0 here, the first flip-flop will get the preset, that is 0, and clear for the second, third, fourth stages, that is also 0. That means if all the stages are getting 0, but for the first stage, if we give the ORI to 0, so we are setting it to 1. So the first stage it will enabled with 1, the remaining all are zeros. That means we don't want to set that 1 bit data in the next stages. We are setting in this 1 in the only first stage, but we have to maintain the all 3 zeros in the second, third and fourth stages of the flip-flops. So that is why only 1 is installed. That means previously the states are 0, 0, 0, 0. Now after installing, after enabling the ORI is equal to 0, so that preset is 1, but remaining that clear is maintaining the zeros. That means preset is 1 means, so it enables the Q0. The first stage is Q0 here, that enables the Q1. That means forcefully we are adding this 1 to Q0, and forcefully we are adding Q1, Q2, Q3 to 0. This is the technique in the ring counter. So if we know this technique, definitely the first stage after the initial stage 0, 0, 0, 0, it will shift to, if one clock cycle is there, it will shift to 1 triple 0, 1 0 0 0. Now after second clock cycle, if the second clock cycle is enabled, so it will leads to the 1 will shift to the second position. That means 0 1 0 0. This is the second stage. Next, if again we will apply other clock signal, so the 1 will move to other shift. That means 0 0 1 0. And if again we will use that whatever the clock signal, so it will leads to 0 0 0, that is 1. And finally the next clock cycle, so again this 1 is given to the feedback of the first stage. So this here the 1, that is why the 1 triple 0, which is nothing but the repetition of the first stage. So here we are using the 4 stages. That is why we are getting this 1 triple 0, 0 1 double 0, 0 0 1 0, 0 triple 1, triple 0 1. So these 4 stages we are getting. So for any stages we are using these flip-flops. In order to increase the flip-flops, we can increase the number of states also. Now this is the overriding input. We depending on the overriding only, here I have given the clear information. So if we apply the whatever the ORI 0 here, so that 0, so simply the preset is 0, but forcefully that Q is set to 1. That means here the first stage is Q0. Now clear signal, whatever the ORI is 0, the same ORI 0 is given to all the 2, 3, 4 stages. That means for the clear signal, so clear signal is again 0, but forcefully the flip-flops, whatever the second stage, that is Q1, the third stage, that is Q2, and the fourth stage, that is Q3, forcefully the data, that is 0, is given to the Q2, Q1, Q2, Q3. So this is the technique. Now preset, wherever 0 is there, Q is directly to 1, and clear 0 is there, now Q is equal to 0. This is the technique in the ring counter. Now coming to, this is the truth table. So whenever the ORI, which is nothing but override input, is low, so irrespective of clock signal, because this clock signal we call that one as a don't care condition, so no need to apply the clock signal. If there is no clock signal, so we are simply assigning the 1 for the first stage. That means Q0 is equal to 1 at that time for the low signal. So Q1, Q2, Q3 are at 0. Now if ORI is high, now that 1, that means simply these are disabled, the whatever the preset and the clear signals are disabled. Now so 0, that 1 is shifted to, because the clock signal is shifted to 1, 1 is shifted to second stage, and in again if the other clock cycle is there, it shifted to next stage, and other clock cycle it shifted to the next stage, and for other clock cycle it shifted to the previous state, whatever the cycle is possible in this situation. So likewise we are giving the waveforms also. So this is a clock signal, from here to here the one clock signal, here to here the other clock signal, here to here the other clock signal, here to here the other clock signal, from here to here the other clock signal. So totally here we are using 5 clock cycles. So for 5 clock cycles, here the first clock cycle we are enabling, that means the data 1 is enabled, but remaining all the stages are 0, triple 0, that Q here QA is nothing but the here Q0. Now Q1 is nothing but the QB, Q2 is nothing but the QC, and Q3 is nothing but the QD. So whatever the 1, this 0 and this 0, this 0. That means these 3 are in that clear signal, and the only one here, this is a preset when the clock signal is enabled. That is the concept. Now for second clock cycle, this QA, that 1 is shifted to this position, and remaining that this 0 will go to this position, and this 0 go to this position, and this 0 go to this position. So it will move like a cycle. Again, for next clock cycle, that is third clock cycle, this 1 goes to this one. Here the QC is 1. Now this 0 moves to here, and whatever the 0 here, it moves to here, and whatever this 0, it moves to here. So likewise, the clock cycle, whenever the clock cycles are increased, the signals are like this. Now components and signals. So preset and clear signals are clear here. That means these two signals we are connected to ORI. Now depending on the FF0, the first stage, PR is equal to 0 and Q is forcefully 1, and if that clear is equal to 0, that is F1, FF1 and FF2, FF3 are forcefully given to the Q, that is 0. So here the first stage is given to 1, the other 3 stages are given to 0 with the help of this ORI signal. So that is the only technique here. Now coming to the advantages of this ring counter. So the simplicity, first one is simplicity, because it's easy to design, because when the number of stages are increased by increasing the flip-flop count, so that is for small purpose it is very advantageous. And low resource use, because we know already only flip-flops is required, but not other signals or other any devices. And predictable output. So because if we start from 1 0 0 0, so next stage we can simply predict, that means 0 1 0 0. So we can predict, because this is a 4-bit, so output is also 4-bit, but only the thing is for one clock signal the 1 is moved to next stage. So we can easily predictable, the output is predictable, and easy to decode, because this is a decoding concept. So we can, each state is distinct and easy to decode, because it uses one hot encoding, only one output at a high at a time. That means if we consider the output, only one output is highlighted. That means in this particular output only one is there. Here particular output only one here. If the next stage is there, so only one output is here, and if the other state is there, only one output. So we can easily calculate, easy to decode the output, and glitch free. So we can easily access, because the flip flop at a time the output is 1. So that is why we can simply enable the inputs, and we can take the outputs. So that is why we can easily make, there is no chance of glitches here. So that is why we can easily access the data at the output side. Now disadvantages, coming to disadvantages, limited states, because we call this one as a limited state, means this completely depends on the number of states of the flip flops. So number of states is equal to number of flip flops. So definitely we have to concentrate on the number of states. So not for complex patterns. So if we want to, we call that one as a random, if we want that random signal, random counts and non-binary patterns, this is not suitable, because this is a binary sequential circular, that means ring counting, but not the random counting or non-binary patterns. Non-binary means any hexadecimal or octal or decimals. So needs initialization. So needs initialization means initially all the states or all the outputs Q0, Q1, Q2, Q3 are at 0. If we don't give any one inside this, in whatever the given data, it will rotate. That means that all zeros are rotated, but there is no data. We cannot predict the output. If we want to install that one, we have to needs initialization. Definitely we have to initialize that one, introduce that one in for the first stage. That means 1,000,000. Then only it will shift to 1,000,000. Now hardware cost increases. Definitely if we want to increase the states, definitely we have to increase the flip-flops. So that leads to increase in the hardware. Now coming to the application part. So ring counters are used when you need a system that goes through a specific repeating set of states. We know already. So for example, so sequence generator, if we want that sequence. So sequence is nothing but 1, 2, 3, 4. So depending on this one shifting, we can simply call this one as a sequence generator. So depending on the sequence shifting only, we call this one as a sequence generator. So likewise, we can simply use this one for time control, timing circuits. So control systems, ring counters are great for things like multiplexers or encoder circuits, where the order of operations needs to follow a certain cycle. So most of the time, we have to concentrate on the waveforms here. So for waveforms, so for each and every clock pulse, or depending on this multiplexer inputs, so the switching is important. That is why we mostly these are this ring counters are the application part for the whatever the controlling systems. Simple design. So as we know already, we have to enable the one and design, understand, because each state has only one flip-flop. So each state has only one flip-flop that is set to 1. So that is very easy. Whatever the design is very simple, because one flip-flop is there. Coming to the finite state machines. So finite state machines is nothing but most of the devices, we call this one as a finite state machines. Coming to this vending machine, we know that ATM machines or coin collector or coin distributor machines, we call this one as a like vending machines. So nowadays these are available in our public places. So most of the time we used these ring counters inside that vending machines, and also elevator controls. So most of the time elevator controls also these type of ring counters we are using. So shift register based applications. So this is a topic, ring counter, but most of the time a counterpart is also there and registers also there. Anyway, we have to discuss that flip-flop concept. So these 3 flip-flops are used for these 3 concepts. So ring counters are a special type of shift registers. So they are used where shift registers are needed for data movement. So most of the time for data movement we are using this type of ring counters. In order to, if we want to give the final output, that means last output given to the first output, then we call that one as a ring counter, or otherwise we call that one as a shift register. The only difference is, that is the only difference. That's all. So next, the summary. Coming to the summary, so a ring counter is a type of shift register in which the output of the last flip-flop is fed back to the input of the first flip-flop, forming a closed loop. It contains a single logic, that is either 1 or 0, that circulates through the flip-flops on each clock pulse, producing a fixed and repetitive sequence of states. Ring counters are simple in design, provide easily decoded outputs, and are widely used in timing circuits and also the sequence generation and control applications. However, they require more flip-flops than some other counters and must be properly initialized to ensure correct operations. Thank you.